My pleasure to have David Hogg today. So David is a professor of physics and data science at the Center for Cosmology and Particle Physics in the Department of Physics at New York University. I'm sorry I'm using Node because he has a big resume. And he's also a senior research scientist at the Center for Computational Astrophysics at the Flatiron Institute in New York. And he spends part of each year at the Max Planck Institute for Astronomy in Heidelberg, where he's a visiting researcher. And his research has ranged across fundamental cosmological measurements, stellar dynamics in the Milky Way, precise measurement of stellar elements abundances, and extrasolar planet discovery. His work also includes a significant engineering component in areas of instrument calibration, automated data analysis, and statistical inference. He's a developer and supporter of open source software projects and open data initiatives. And today he's going to talk about machine learning and tell us if it's good or bad for science. Thanks.
Thanks, Gabby. I'm going to use this. Good, thank you, Gabby. Good, I was asked to quickly answer this question, and I'm afraid my answer is not quick to this question. And I should say before I start, this is all stuff I've done with Soledad Villar, who is a mathematician at Johns Hopkins who works on fundamental issues in machine learning. And some of the work that I'm talking about here is in applied math, really, but I'm very interested in the applications to physics. I'm trying to talk in a way that's useful to people across social sciences and natural sciences, but we'll see. Feel free to interrupt me. There will be some astrophysics in here because my examples are astrophysics because I'm an astrophysicist, but I've tried to make it as general as possible. So I'm going to start with an astrophysics example just to give a sense of what I consider to be like an important scientific result. I would say the thing we most confidently know about the universe is that it is expanding. It's a very well-established fact. We observe galaxies around us. All the galaxies around us are moving away from us. The ones that are more distant are moving away faster. And so we can see that the universe is expanding. And an important fact is that in general relativity, all solutions for a homogeneous universe either expand or contract. So there's also kind of a theoretical understanding that the universe ought to be expanding. So we see that it is expanding, it ought to be expanding, and there's countless experiments of all sorts of kinds that support the expansion. So I consider this to be one of the scientific facts we best know. Okay? And so now the question is, no machine learning was involved in this. In fact, this was established in the 1920s before the words machine and learning were being used simultaneously. So now the question is, have we learned anything in science from machine learning? How does machine learning support discoveries in science? And I would say right now, there are not many things you can put on this list where science has really been moved forward by machine learning. But one example that people often say to me is, well, machine learning solved protein folding. And I don't know if people know this result, but I think this is one of the most famous applications of machine learning in the sciences, and it's a very important one. This is AlphaFold. This is DeepMind, which is this is done by a company, not in an academic lab. In fact, the engineering effort behind this was so large, you could not do this in an academic lab. This involved hundreds of people paid enormous salaries at DeepMind. And what they achieved in AlphaFold, and there's a whole set of publications, that's just one of them, but what they achieved is if you give the AlphaFold a sequence, a protein, or RNA sequence, then AlphaFold can predict the structure of the protein that will fold from that sequence. And this is a very important result because people had not been able to do this previously. However, my assertion is this actually hasn't told us anything scientific about how proteins fold, because the AlphaFold system is an enormous black box. It's a machine learning method that was trained on an enormous number of known conformations of proteins and known sequences of proteins, and AlphaFold learned how to generalize that and make predictions for others. So it's a huge achievement, but I would say that this achievement is an engineering achievement or a clinical achievement that allows us to function, but doesn't actually explain to us how proteins fold. And so I'm sort of comparing these two results, the expansion of the universe and this, to make a point. And before I get to that point, I just want to say, why am I talking about machine learning and not artificial intelligence? So I'm talking about machine learning because I know nothing about artificial intelligence, and I work with machine learning, and I'm going to define in a minute what machine learning is. But I'm not going to talk about the current trends in artificial intelligence. So I'm not going to talk about ChatGPT or Claude or any of these language models that people are kind of very excited, and they're definitely disrupting lots of things. I personally work on precision measurement. I do data analysis, and all of the areas that Gabby mentioned that I've worked in are all areas where making measurements is paramount, and making precise measurements is paramount, or the data are very hard to use. And I'll give some examples as we go. And precision measurement is an old thing. In fact, astronomy is the first area of precision measurement. You might remember that people gained power by being able to predict eclipses and things like that. Well, that's a precision measurement question. When is an eclipse going to happen? And then in astronomy, and I think in all of the sciences, machine learning started entering into measurement making in the 1990s. And we used it in a big project called the Sloan Digital Sky Survey, and I could explain that afterwards. And I'm going to give you examples that are astrophysical as I go. And I would say, actually, I haven't defined machine learning yet, but when I define machine learning, I'll give you a sense of why it goes back to the 90s or earlier. It really goes back to the 70s, but its use in science goes back to the 90s, I think. So what I'm going to say on the negative side, the answer is there isn't a simple answer to whether it's good or bad for science. On the bad side, I'm going to say that current machine learning methods are not trustworthy, and trust is a big problem. We don't know when they are hallucinating or telling us things that aren't true. Their use of machine learning can expose you to biases or systematic errors, which you have to understand and can't be understood in some cases. On the positive side, most scientific projects are big engineering projects now, at least in astronomy. Our projects are very big engineering projects. We literally build huge machines on mountaintops that observe the sky. And those engineering systems require flexible, fast machine systems. And I'm going to talk a lot about calibration and backgrounds and auxiliary things, as it were. And causal. I'll say some things about causal that are very positive. Okay, good. My group, just to give you a sense of who I am, I do a lot of engineering because I do precision measurement. Precision measurement is about designing projects and then designing data analysis plans that will deliver high precision. So I do a lot of engineering. I do instrument calibration, and I operate observatories, and I build pipelines. And as Gabby said, we support a lot of open source software. My group is in some ways a software group. And I think that engineering is essential to science, and I think that I love engineering, and I love working with engineers, and I consider myself an engineer even though I'm trained in physics. But engineering successes, I think, are not the same as science results. So I'm going to make some distinctions as I talk about engineering versus science as we go. Good. So I'm now going to define machine learning. Who here would say that they have used machine learning in their work? Okay, good. That looks like it's about a quarter of the room. Some of you who've used machine learning in your work will not agree with this description. Actually, when Soledad Villar and I wrote a paper about this, we wrote a paper about whether machine learning is good or bad for science. And in the paper, we literally said these areas of scientific inquiry are bad. And we're literally saying, don't do these things. So we were directly attacking particular lines of inquiry. But and we got tons of emails saying, you're wrong, you're wrong. But every email that said we're wrong was only objecting to our definition of machine learning. It turns out what I'm saying now is the most controversial thing I'll say in my talk. I don't know why. But this is my definition of machine learning. A machine learning method is a method whose capability improves as it sees more data. So this is something where it's a machine that takes in data, and as it takes in more data, it becomes more capable. That's a machine learning method. And in that sense, you can see these LLMs that I said I'm not going to talk about as machine learning. Some of the people who work on those LLMs would say that they work on machine learning, and the data they're taking in is text, and they're becoming more capable at predicting new text. There's some details about scaling here. The machine learning model, to be a machine learning method, you have to scale faster than the square root of n in a certain sense, which is a technical issue, which I'll debate with you if you're a statistician. The last time I gave a talk in this area in front of statisticians, that was like a good 15 minutes of argumentation. And there are these classic methods which date back to the way before the 1990s, but they first started being used in science in the 1990s, and those are in like the natural sciences, and those are principal components analysis, independent components analysis, support vector machines, linear regression, Gaussian processes. Those are all things that have been around for ages, and people have been using them for a long time. And those are all workhorses still of machine learning. And now many people don't believe that those things should be called machine learning. Those methods are too simple, but they meet my criteria, so they are machine learning from my perspective. And in fact, they're often swap-in replacements for sophisticated machine learning methods. And of course now there's tons of sophisticated machine learning methods, multi-layer perceptrons and CNNs, and now transformers are what power those LLMs. Good, and then this is just the standard, just to remind you of where machine learning lives. Machine learning lives, there's two kinds of machine learning, supervised and unsupervised. I'm just gonna show the supervised case here just to put people on the same page of what kinds of things we're talking about. The idea is you have a training set of data, which is some large set of data, which counts as kind of your ground truth. There are a set of example objects where you have data on those objects and maybe labels for those objects, and you believe that those data are representative and those labels are correct. And then you try to find a function, and all of machine learning can be seen as like function finding or function search. You try to find a function that does the best job you can of predicting the labels in the training set. And then now, if you are given new data, which is the test step, you can predict new labels for any new object by just applying the function that you learned from the training data. And that's kind of the classic setup for supervised machine learning. And there's a deep assumption, well, there's two important things to note, is you need to give this function f of x an immense amount of flexibility because you don't know what it's gonna need to do in advance. You don't know. If your data are YouTube videos and your labels are contains a kitten, you don't know what the function is that's going to take the YouTube video and tell you whether or not it contains a kitten. So you need a very flexible function there. So that's the first point. And the second point is you have to assume deeply that the test data that you're going to run it on are similar to the data you've seen before. If all the data you trained on were American videos of kittens and all the data you test on are Slovenian videos of kittens, things can go wrong. Good, and so machine learning has effectively a very narrow philosophy. Machine learning methods fundamentally are methods that are purely empirical. They are just relate data to data. They take in data, they learn about the data, and then they operate on new data. That's it. And so in machine learning, it's kind of the case that only the data exist. There aren't other principles in play. There's just data and data in, data out. That's it. And then importantly, we don't really need to understand what's going on inside this function f of x, which I remind you is a very complicated function. We don't know what's going on inside there. And then there's a kind of an epistemological point, which is that the only way to know at some level that a machine learning method is working well is that it does a good job at predicting the labels of held out data. That's the way we know that it's working well. So the question of, is your model good? If you ask somebody, oh, you use machine learning on that, is it a good model? Their answer is, it predicts well. So it's like in the AlphaFold case, we believe that AlphaFold model is a good model of protein structure. How do we know that? Because they applied it to new sequences and predicted their structures, sequences that were not used in the training data. So this is incredibly different from the epistemology of physics, right? In physics, it's all about, like, does it conserve energy? Does it obey symmetries that we care about? Is it consistent with field theory or general relativity or quantum mechanics? Like, our considerations about whether a theory is correct have all sorts of properties that have nothing really to do with data. They have to do with, like, theoretical consistency. And all of our interests in physical theories are about latent things, things that aren't data. We care about, like, what is the entropy in this room? What powers the interior of the sun? Those things are not directly observable. They're like latent properties of the world. They're not data. It's their theory. They're like a mix of, like, empirically constrained theories or something. So it's a very different ontology and epistemology in science. Good. So going back to this example of the expansion of the universe, which I talked about at the beginning, when we measured the recession velocities of these galaxies and looked at the relationship between the recession velocity of galaxies and their distance from us, we were doing things like measuring the expansion rate of the universe. We were estimating the age of the universe. We were testing a fundamental prediction of general relativity. We were not primarily trying to predict new data. It happens to be that the expansion of the universe model does predict new data, but that wasn't really our goal. The Nobel Prize doesn't go for predicting the velocity of a new galaxy. That's not where the scientific interest is. Good, and so another sense in which, if you look at what are the contrasts or conflicts, this is sort of the section of this seminar in which I talk about, like, the conflicts between machine learning and science. If you look at, so machine learning methods use these sort of train, validate, and test frameworks, which, by the way, are very statistically clean. One of the things that's interesting is if you only have the data, if the data are the only thing you don't have any other way to test the truth of your model or test your model, you have to be very careful statistically that you're making good statistical statements. And the machine learning community is actually, by and large, pretty good statistically relative to other sciences, because they have to very clearly split the data into held out and use data to do the comparisons. But science does not really use this framework because we're usually trying to find really new things that are not held out data, but completely new things. We find all the quasars that are near to us, and now we want to find all the quasars that are far from us. You know, that we're trying to always extend to new regimes. And then machine learning takes the data as given, where we tend to care about experimental design and noise models and so on. So the machine learning has this very kind of passive, is kind of very passive in this sense. Okay, finally, I want to make a comment about interdisciplinarity. I'm a big believer in interdisciplinary research. In fact, I'm one of the founders of the Center for Data Science at NYU, and I care very much about people from different disciplines working together. But there is a kind of paradox here, which is that machine learning methods were designed for very commercial applications. Like, literally, they're trying to predict which TikTok video you want to see next. And, like, does that kind of question map onto scientific questions we care about? It's not obvious. But I have to say, TikTok is extremely good. I think TikTok is one of the best recommender systems that's currently operating. And so, you know, is presenting content to users in any way similar to the kinds of questions I'm answering in astrophysics? The weird thing is the answer is going to be yes to that. That's the weird thing. Okay, good. So I want to talk for a little bit about trust. So the next section here is going to be about trust. How do you trust the machine learning method? And I'm going to say that we don't, and we actually don't know how to trust them right now. So internally, we don't know what machine learning methods are doing, and it's fundamentally because it's this extremely flexible model. So the kinds of models that people are using in machine learning methods right now will tend to have billions or even trillions of parameters in them if you think of it as a parametric model. Actually, machine learning people don't tend to think of it as a parametric model, but if you think of it as a parametric model, it has billions to trillions of free parameters. And so the models, and with tons of internal degeneracy, so it's almost impossible to interpret what's going on. And I actually think it might be literally intrinsically impossible to ever understand what they're doing inside. This line here, that interpretability is a failure, makes some people upset in my world, because some people work on this, interpretable machine learning methods, but there really are not current interpretations. And I think whenever you find that a machine learning method is interpretable, we'll just make more complicated ones that will meta up the methods, and so they'll become uninterpretable again. We always want a very flexible model. And so I don't think we're ever gonna really know what's going on inside. So you're not gonna trust it by looking under the hood and going, oh, what did it do? The question that arises is, where can we use models that we don't understand? And I'm gonna surprise you at first. At first I'm gonna say, you're gonna think I'm saying you can never use things you don't understand, but then in the second half, it's gonna be different. Okay, good, so here's an example. This is out of date. This example is extremely out of date, so I apologize for this, but it's just an example that has a nice visual that I wanted to show. So the thing on the left is a simulation of the universe that cost tens of thousands of hours on a supercomputer. So it's a simulation of a chunk of the universe that goes from the initial conditions of the universe using gravity and predicts what the structure in the universe will look like at the present day. So this is like how we do cosmology. It's all based on simulations these days. There's a theory of cosmology, but the theory is fundamentally a computational theory, and we can compute what the present day universe should look like. This is a very large scale structure that's comparable to the size of the whole universe. I mean, it's like a few percent of the volume of the whole universe over there on the left, and it's a simulation that took ages. Now, the thing on the right is a prediction that can be executed in under a second on a laptop. And this prediction here is just the execution of a machine learning model that was trained on a set of these n-body simulations. So the idea is you do a bunch of these extremely expensive simulations, and then you train a machine learning model that can generate examples that look like the simulations you did, but are different. And if you look in detail, they're different. These two are not the same. This is supposed to be a draw from the same distribution of these simulations. See? Now, if this works, this is incredible, because we are burning lots of carbon to produce those simulations, and if we can do them very fast, this is great. And the simulations we do in cosmology are very expensive, and depending on your attitude towards astrophysics, possibly useless. Good, so I want to say something about what this looks like, and this is a change of subject, and look how old this is. This is from 2015. 2015 is like the 18th century, like when it comes to machine learning. So this is like ancient history. But this paper in 2015 was extremely influential and actually led to a big literature. I actually said the other day that the literature in adversarial approaches to machine learning is comparable in size to the full astrophysics literature per year. So this is like a really important, this discovery was a very important discovery. It's the discovery that when machine learning methods are extremely flexible, they have really weird properties. You're talking about a very high dimensional function that you can't interpret. So it can do some weird things. So what's this? So back in 2015, which was a long time ago, there was a set of benchmark image classification systems. I don't remember which one this was called, but this was one of the benchmark image classifiers that was a world leader in 2015. And it could take that image there and identify that that image was an image of a panda with reasonable confidence. Not high confidence, but reasonable confidence. Good? And then the people who wrote this paper did a lot of hard work and found this noise pattern, and they found they could add a tiny multiple of this noise pattern into that image, and they would get that image there. And that image is not the same as that image. It might seem the same, but they're not the same. This is a different image. And when this image was put through the classifier, at high confidence, this is a given. And this behavior, which this is an adversarial attack, and you might think, okay, well, that model is a really weird model, then whatever. This behavior is completely generic. All sufficiently complicated machine learning models have these behaviors, these adversarial behaviors. And in fact, this paper launched a huge literature, some of which said, oh no, this is a feature, this is a good thing. But I just want to say a few words about it from the point of view of a scientist. So from the scientist's point of view, well, first of all, people here know what a given looks like? Nobody ever knows what a given looks like. So I know what a given looks like, and because I've given this talk a million times, but I believe that the nose of the panda looks like the face of a gibbon. So if you look up, yeah, good, you're looking up a picture of a gibbon, yeah. Everyone in the room, this is where everyone in the room opens their phone and looks up a picture of a gibbon. Don't do that. But anyway, here's what I think. Am I right? Kavi doesn't believe me. Anyway, here's the thing. When I look at that image over there, first of all, when I look at that image over there, I'm pretty confident that's a panda. I'm more than 57.7% confident that's a panda. So, and image recognition has gotten so much better since 2015. Now image recognition systems would get that at very high confidence. That's not a difficult image. But when I would say, the reason I would say that's a panda is it's like a creature with off-white fur, with black around the eyes and black ears, and it's in a tree. That seems really panda-y to me. And then when I look over here, I see a creature with off-white fur, with black around the eyes and black ears, and it's in a tree. So I also, at very high confidence, would say that's a panda. So I think what this reveals is that the machine learning methods are not doing what you think they're doing. They do impressive things, but they're not doing quite what you think they're doing. By the way, there's a lot of work in this adversarial attack area now. People are wondering if you can like wear something that would cause a self-driving car to crash. And people are working on that. Could you design clothing that makes self-driving cars crash? That is an interesting question, and it's obviously very important. And it's the same question, you see why? Because we need to trust self-driving cars, because you might be passenger or pedestrian, but I also want to trust anything I'm using in my measurement. I'm doing precision measurement. I can't be throwing things in that do things I don't understand. Well, we'll see. There can be some funny. Okay, good. But this must have implications for this. You see, because is this producing this, like something that looks like this for a good reason or a bad reason? Okay, good. I turned everything off. Oh, I hit the off button. Oh no, I'm good. Okay, good. So what do these adversarial attacks reveal? I don't know, not everyone agrees. They are very carefully tuned attacks. They are not generic attacks. These are very carefully tuned things. So they're not generic failure modes. It's not like every time you add a little noise to an image, it screws up. That was a very highly tuned piece of noise. But I think they reveal, as I said, that the model is not doing what we think it's doing. So we can't trust machine learning. That's my position right now, and we need to figure that out. I think this is a to-do item for the community. I don't have a solution. I'm not gonna be like, oh, here's how we trust machine learning. I'm not. I'm gonna give some suggestions at the end, but I don't know. Okay, good. And I just want to make a very technical point, which is sort of off topic. But by the way, whenever we use these emulators, we're using them when the simulations are incredibly expensive. So I work a little bit in cosmology, and I work a little bit in earth science. And in earth science, the earth science community could easily use all of the scientific computing capability of the entire world. I mean, climate is a very important issue, and the atmosphere and the oceans have dynamics at all scales. So really, we could use it all in climate science, and in earth science, we could use all of it. And so we're using these emulators because simulations are incredibly expensive. And that means that there's kind of a confirmation bias issue here, which is that you can only check a result if it's very, very valuable to check the result. Because checking a result would be very expensive. If you did everything with emulators that run in a few milliseconds, and now you need to rerun with simulations that take 10,000 hours apiece, and you might have to do 10,000 of them, it becomes prohibitive to check results, which has some issues for. There's another technical point, which I'm not going to talk about, but I would talk about if this was a statistics audience, which is that machine learning methods are optimized for prediction accuracy. The goal is to accurately predict that that image is of a panda. It's not to make scientific measurements of that image and report like the likelihood or something quantitative about the panda. It's trying to make bets. It's basically trying to win bets. Actually, Bayesian reasoning, if you use Bayesian reasoning is optimized to win bets. And whenever you're making predictions and you intend to win bets, you use biased predictions. And usually in scientific investigations, we actually want unbiased measurements. We want to know, what does this data set say about this parameter? And so measurements and predictions are kind of in conflict. And if you look at the paper that Soledad and Villar and I wrote about this, it's called Is Machine Learning Good or Bad for the Natural Sciences? If you look at that paper, we have an example in the appendix that shows very clearly that predictions are not the same as measurements. And that's a very technical point, but which is, if people want to ask me more about it, I can say more about it at the end. Good, so I asked, where in science can you use a model you don't understand? And it sounded like everyone thought, oh, I'm saying, oh yeah, don't use things you don't understand. But actually, we use things we don't understand all the time in science. So in Europe, for instance, the European Space Agency launched the Euclid spacecraft, the Euclid spacecraft that is observing the universe and making cosmological measurements, and it involves infrared detectors. And I know the infrared detector team on Euclid, and they don't understand exactly how their infrared detectors work. There's some weird issues with the infrared detectors that they can't understand. And what they're doing is they're using an empirical approach to understand empirically how the detectors work and correct the data for the empirical issues with the detectors. That's how we work. In science, we do this all the time. If you use a microscope and you take a recording from that microscope with a CCD, that CCD will have a flat field and bias variations and gain variations and so on, some of which you understand, some of which you don't. But you can correct for them. So we use actually models we don't understand all the time in physics and in all of the sciences. And we deal with those things empirically. We use flexible models to deal with them empirically. And notice that's starting to look a lot like machine learning. So by the way, I don't know how many people think kind of about causal or about statistics issues. Like, one of the things that's funny about doing data analysis, I do precision measurement and I do engineering, and it sounds like the most technical thing you can possibly do, but it's actually the most philosophical thing you can possibly do, because whenever you're doing data analysis, you get into these weird philosophical issues. And one of the important philosophical issues that comes up in data analysis is causal questions. Most of the questions that we're asking as scientists are fundamentally causal questions. And as you know, causation and correlation are related in a complicated way. Some people like to say correlation doesn't imply causation, which is true, but certain causation models do imply certain correlation properties. And so there's this sort of big, complicated thing in statistics that's very important in the social sciences and in the health sciences called causal inference. And you know lots about causal inference because it's things like, does this vaccine work? How can we know whether this vaccine works if you can't do controlled trials and certain things like that? In the physical sciences, it's less true that people use this causal inference language, but we actually are making causal claims all the time. We see a star vary. Did the star vary in its brightness because of the instrument or because the star actually varied? Was it caused by the star, or was it caused by something in my instrument? Or we have atmospheric absorption. You're observing a star, it's getting fainter. Is it getting fainter because the transparency of the atmosphere is changing, or is it getting fainter because because the star is actually getting fainter. So we ask causal questions like that all the time. And also counterfactual things. A lot of science is about counterfactual things. If I had applied this to my sample, this would have happened. So here's this brightness of a star example. So this, I don't know, how many people here have some footprint in astronomy or astrophysics? Good, okay, about a third, I would say. So an embarrassing thing about astrophysics is there aren't that many things we can observe. Like we gather photons, that's basically all we do. So a lot of astrophysics comes from very precisely measuring the brightnesses of stars, which is absurd. We just measure the brightness of a star very accurately. In terms of, if you can measure a star very accurately in its brightness, you can learn a lot of things. That's how we know the interior structure of the sun. We measure its brightness very accurately over years, and we can see the normal modes of the sun and learn the interior structure. It's also the way we found most of the planets. Most of the planets that are currently known were found by very carefully measuring the brightness of stars and seeing the variation when a planet passes in front of the star. And so there's a lot of questions in astrophysics that boil down to, can we understand what variations in the brightness of a star are due to the star and what are due to the instrument you're observing it with? Because we're asking questions, well, I'll show you data in just a second. Good, I just want to make this point, which is going to be related to something later, which is that you can make the best possible argument, the most conservative argument that this variation is from the star if you put a ton of flexibility into the instrument. So if you make your instrument model extremely flexible, so your instrument can do a lot of different things, then if you see a variation that the instrument can't explain, it kind of has to come from the star. See, there's kind of conservatism here. If I want to be very confident that a variation came from the star, I want to put a lot of flexibility into my instrument. Totally, it's going to advance. Oh, I think PowerPoint is about to give me trouble. Oh no, I think we're good. Okay, good. So here's an example of a star. This is a measurement of brightness variations in a star. The top panel is the measurement of the brightness of a star over an 80-day period. This is like an 80-day period. And this was measured with the Kepler satellite spacecraft, the Kepler spacecraft, NASA Kepler spacecraft, in a late phase of its life where it was disabled in a certain way. And this variation you see at the top is it's the brightness of a star as a function of time for the 80 days. And you can see it's very choppy. But actually, if you look at the y-axis is in parts per million. So this brightness of this star is actually very stable. And there's this choppy variation that you see there. Now, is that choppy variation due to the star changing, or is it due to the instrument? Well, the green line, I don't know if you can see it back there, but the green line that's drawn through those black points is a machine learning model for the K2 mission instrument properties that was trained not on this light curve. That's a prediction for this light curve. So we were able to predict almost all of those variations just by considering the instrument without using the star at all. So almost all the variations you see up there are actually variations due to the instrument, not the star. And when we subtract out that instrument model, this is the brightness of the star as a function of time. And you can see the axis scale has changed completely. And this is now very well measured brightness of the star. But you can see that green line is a very, very complicated model. You see, we had to put a ton of flexibility into the instrument model to make a confident measurement of the brightness of the star. By the way, this model, I just said that nothing's interpretable, but actually this model is very highly interpretable. Every spike in that is a thruster firing. Every spike in that matches up with a thruster firing on the spacecraft. And every spike over here does. And they reverse sign, you see, between this side and this side. And it has to do with the fact that the spacecraft goes through a zero solar torque point at this middle point. So they fire the thrusters on one side of the spacecraft over there and on the other side of the spacecraft over here. So actually the crazy thing about this model is in the end, it is actually highly interpretable. But this is a model that has, I don't even know how to count it as hundreds of thousands of free parameters. I'm not sure how many free parameters, but that's a prediction for that star. Come on, baby. Can totally advance. Good. And so I just wanted to make the point that machine learning methods are valuable in these calibration tasks because the machine learning model does exactly what we want for the calibration task. We want a flexible model to model our instrument, and machine learning models are maximally flexible. By the way, so another place where we do causal kinds of questions. So one causal question I just asked was like, is this variation from the spacecraft or from the star? Another kind of question we ask is, is the signal we're seeing from the astronomical object or something that happened along the line of sight? And I think I have an example here. Yes. So on the left panel, those black dots are data. These are spectral data now. So this is measurements of the brightness of a star as a function of wavelength. And you can see it's a very tiny wavelength range. You see it only goes from 6302 to 6314 angstroms. It's just a tiny little wavelength window. But this is part of a huge spectrum. Actually, this spectrum has 500,000 pixels. It's an immense spectrum we take of a star. And we took these spectra to measure the radial velocity of the star. We're measuring the radial velocity of the star. And the red curve and the blue curve are machine learning models. The red curve is for what the star is doing, what the shape of the stellar spectrum is. And the blue curve is the shape of the atmospheric absorption of the star. So meaning in our own atmosphere. So the absorption features in the red curve are coming from the photosphere of the star, and the absorption features in the blue curve are coming from our atmosphere, from the air. And you can see they're in doublets, and if you know things about chemistry, you'll know why they're doublets, but I don't. It has something to do with rotation of molecules. I don't know. But anyway, that red curve and that blue curve are machine learning models. There was no physics in those models. They're just pure flexible machine learning models, and they were trained on data that was not these data. They were trained on held out data. And the way we were able to separate into the star and the atmosphere is that as the Earth goes around the sun, sometimes it's Doppler shifted towards the star, and sometimes it's Doppler shifted away from the star. And so the star and the atmosphere move with respect to each other. And so we were able to use a lot of data to do this separation. But the separation works because both models are extremely flexible. And then this model over here is independently trained model, same region, but on a different kind of star. That star is very similar to the sun. The one on the left, the star is very similar to the sun. It's actually 51 Peg, which is the star that first showed planets. This is part of the data that was used to discover the first planets in 1995. Though we didn't have a model this sophisticated in 1995. And then this is Barnard's star, which is one of the nearest stars to us, but this is a much cooler star. It has much more absorption features, but still we can separate into atmospheric features and stellar features just by having a very flexible model and some causal beliefs about what can cause what. So anyway, these are just examples of things where, like, when you need a flexible model, there's lots of places in science where you need a flexible model. We don't need to interpret those models. We just need them to be accurate. And they are very accurate. Good, so just to finish this part, there's a conservatism point, which I mentioned earlier. It's generally considered like cavalier or like crazy to throw machine learning into your data analysis, but it is not crazy. Some parts of your data analysis, actually, it's the most conservative thing to put in very flexible models. If something's a nuisance and you want to show that it isn't affecting your data, putting in a flexible model actually leads to more conservative inferences. Good, I mentioned this earlier, but I just want to emphasize it because I think it's such an important point. It is very obvious that we are headed into a regime where we're going to use machine learning methods to speed up computations and to emulate things. Everyone's doing that. In fact, Andre in the front row over there just told me that he just built an emulator for one of his slower pieces of code. And now it's fast. So this is an important thing. This is going to happen. It is happening. This is critical in earth science right now, earth sciences. It's so important. We actually have to understand climate change, and we're understanding it partly by using emulators. So this is really a very important thing, and it is happening. So the question is, how can we build systems so that we trust emulators? And I don't know. This is an open question. There isn't currently a very good answer to this question. Right now, they're just being tested, as I said at the beginning, as do they perform well on held out training data, which I don't think is sufficient because of that Gibbon example. And so I'm working on various things in this area. One thing I'm thinking about is exact symmetries. We know that the universe obeys exact symmetries. We know that the universe, like the oceans, the fluid equations in the oceans are a field theory, and field theories have stress tensors and force densities that obey physical laws, and they conserve quantities and things like that. So we're thinking about exact symmetries and conserved quantities. Another thing we're working on is things that involve adversarial training. What if you actually take that the fact that adversarial attacks work and build an arms race where you use the adversarial attacks to build defenses against adversarial attacks and try to make methods that are strong. And then we're interested in the possibility that maybe you could trust your system by doing sparse or actively chosen resimulations or something. So we're looking at questions like that. And that's all joint work with Soledad Villar at Johns Hopkins. And all of the kind of technical things in this talk owe a lot to Soledad. One of the interesting things about all of this is that many of the issues that relate to trust in the physical sciences apply to artificial intelligence in general. You might have noticed people are talking about whether these LLMs are going to buy weapons and take over the world, or start investing companies and buy everything. I don't think that's very likely, but people are very concerned about whether we can trust. I also mentioned self-driving cars. Probably they're coming, and we need to be able to trust those things. And so a lot of the issues about trust appear in artificial intelligence more generally, and we in the sciences maybe have a role in working on trust. And this is what I said. I think I don't have much else to add. I said that machine learning tools have some dangerous properties. They can lead to badly biased outcomes, but there are contexts in which we don't have any choice. One thing is the sort of expensive simulation emulation side. I don't see any way to avoid using tools like this. And on the other, for intellectual reasons, we want to use machine learning methods in these calibration and empirical correction contexts. And it's important to emphasize that the simulation needs of the sciences are bigger than the currently available computing in the sciences. And I think we have unsolved problems to solve if we're going to ensure that the future of these methods is good. Thank you.
Thanks, you're on time. Any question?
Oh, there's a talking stick.
Thank you very much for your talk. It's fantastic. So usually this sort of talks leads me more towards philosophy than science.
Yes.
Even though, okay, so...
Go there.
So
you're allowed. It's a philosophy-safe space.
Thank you, thank you. So the way it started, we started with AlphaFold, and then you went up to interpretability, and it doesn't really work, limited by model capacity and etc. And then eventually you came to n-body simulation, right? So I love particle physics, general relativity. The theories are excellent. They work to finest precision. And now we have some tools that work.
Yeah.
And we don't know how exactly it works. We are trying to work on this. Do you think in the future, the focus from the scientist community should more focus on interpretability of large models, how they work, rather than going back to the old theories and trying to compare with them? Because the reason I ask, very recently there is this matrix multiplication paper from DeepMind that works. Nobody understands how it works. It's fractionally faster. Why we not try to understand why that works?
Good. I'm not going to give you, that's a great question. I'm not going to give you a very satisfying answer to that question. One thing I would say is, like that, the matrix multiplication thing is ridiculous because you'd never think you could emulate matrix multiplication. It's so dumb. It's just like this. How can an emulator help you? So I don't think, well, I have two kind of reactions. One reaction is, I really don't think interpretability is going to work. I don't think, like if that is an enormous transformer or something, no one's gonna pick through that and figure out how it's working. That would take eons. But I have to say, if emulators like that N-body emulator I'm showing you, if that thing really is predicting the statistics of the cosmological density field correctly, something we only know how to predict with 10,000 hours on a supercomputer, then there must be a good idea in there. It must contain a good idea. And actually, when we first started doing the symmetries, I mentioned here that we're thinking about exact symmetries. One of the reasons we were putting in the exact symmetries is we thought that, well, if we put in the exact symmetries, maybe we'll just find out which symmetric tensor operators are producing those emulations. So I think if there's any hope that we're going to interpret what's going on, it has to be by somehow structuring the internals. I don't think you're going to pick through an unstructured model like a transformer and figure it out. But I don't know. That's a great question. That's the question. By the way, I would consider it a huge breakthrough if somebody trained a machine learning model and then realized that there's an easier way to do matrix multiply. But you see, the funny thing about it is what they did is they showed that you can do matrix multiply faster, but nobody knows how. So it didn't move forward human understanding of matrix multiply. By the way, matrix multiply is an active area of research, and there's breakthroughs every few years. And it gets slightly better, but there was what he's referring to is there was a substantial leap. I guess it was this year. It was very recently with emulator.
Another question?
Thank you. So I have two philosophical, maybe even partially rhetorical questions.
Yes, good.
The first one, we talk a lot about trusting machine learning models and we stress test them in crazy ways, like what kind of clothes you have to wear to make a self-driving car crash. Now, what clothes have you wear to make a usual car crash? Any dark clothes in the dark time, right? Yeah. So my question is semi-rhetorical. Can we trust any other method and scientific publications in general, considering that the reproducibility level is horrible?
Good,
and we do not stress test all of them.
Yeah.
So where is the difference? Should we really be so worried about machine learning stuff when we have problems with everything else?
Great. That's such a good question. I love it. Can I answer? Is that okay? So I love that question. Actually, I gave a much more technical version of this to a statistics department at Michigan, the University of Michigan Statistics Department, and it was a great experience because they were just like, what? They were literally saying in the audience, from our perspective, there's no difference between these emulators and any other calculation people do. No, all calculations need to be verified. Actually, one of the things we're very interested in, we figured out this adversarial attack thing is relevant to us, and then we realized, oh, we need to attack just the standard simulations. We should also attack the simulations. And the simulators who we know actually showed us that there will be attacks because they know, there's certain places where approximations it switches from one approximation to another. And if you hit the initial conditions right at that separatrix, you'll totally attack successfully and you'll get wrong answers. So, and you mentioned reproducibility. Actually, one of the things I was asked, or I get asked a lot actually, is how reproducible are these things? And I think there is a kind of mix of things of what you call stress testing, trust, reproducibility, and it applies across all of science. The other thing that the statistician said, which is also relevant to your comment, is that this stuff about confirmation bias. It's expensive to test this stuff. It's expensive to do the stress testing you want to do. And the statisticians, again, were like, that's not different. That's always been true. There's been confirmation bias since the beginning of time. And that is true. I think everything here is also can be somehow applied to all of science. It's just that machine learning somehow amplifies these problems. They're amplified because once you have this emulator, you're like, let's go. And so it amplifies the confirmation bias. It doesn't really change it, I think.
I think that maybe part of the problem is that in many ways it's so easy to trust actually machine learning because it produces such, well, in many cases, kind of semi-magical result, and people who don't work with that often, it's easy to confuse it with like being truthful, yeah? Okay, but my second question is even more generic. I was actually a little bit misguided by the title because when I read, is machine learning good or bad for science, I expect something like, is using machine learning makes us better scientists? Will it lead us? And your talk was more about whether it's useful, and astronomers kind of know that it's useful. Yeah, we use it for the last like 40 years. But my question is, do you think that this advance of machine learning methods in science actually makes science better? Or are we kind of tending to do this kind of numerically based, data-based science, and in this way harm our attempts to find analytical solutions, even when they could have been found?
Yeah, good. That's a great question. There's a big question. Like science is in like I'm not gonna give you a satisfying answer at all. Science is in like a disruptive moment right now, especially in astrophysics. Like in astrophysics, the amount of data we're getting is like rising very fast, and somehow both Europe and the US and China are all building enormous experiments that are producing enormous amounts of data. And we're getting much more data than we have time to kind of think about individually. And I do think there is, like, everything in the world is kind of bandwidth limited. And so as the bandwidth has grown, our data sets have grown, but like human bandwidth hasn't changed. And so there is kind of a question about whether like astronomy is somehow overbuilt. And whether, like, you know, whether human understanding, you know, if you have 10 times as much data, do you produce 10 times as much human understanding? Like, I don't know. And I think there's a real question for the scientific communities to ask, which is about, like, should we think about science as being compute limited or bandwidth limited? Because when it's bandwidth, humans don't enter into that calculation, if you know what I mean. How's that for not an answer to your question?
Well, I warned that my questions will be semi-rhetorical because I understand that there cannot be a satisfying answer. So I'm just like half question, half comment. Actually, I'm going to ask one last tiny question. You said that...
and then Gabby's going to knock you out.
No, it's very easy and very typical question that sounds always, I mean, you know, I know that you said that you won't be talking about LLMs, but your personal opinion, do you think that LLMs will make us better scientists, worse scientists? Are you afraid of students becoming stupider or smarter?
It's funny that you asked that because actually Gabby and I were using Claude yesterday.
No, you were.
Yeah, I was. I have to admit this. I had never used an LLM previously to yesterday, and I used Claude in Gabby's office to check some things that we were working on, and most of the time it was very useful, and then sometimes it gave us answers that were wrong, and we then pointed out to it that it was wrong and it was correct and so on. But it would not have been useful if we hadn't already known a lot about the problem. Like it answered something about a principal components analysis that didn't use the fact that the matrices were unitary, and then we pointed out the matrices are unitary, and I was like, oh, you're right, and it changed its answer. And we were like, and it's similar to coding. The one place where I use the tools is actually not the LLMs really exactly, but it's like Copilot that helps you write code. And even that is only really useful if you're already pretty good at writing code, because it will extend out your code in certain ways, and sometimes it's just not answering the right question. So again, unsatisfying answer, I don't know. It's not obvious to me how to use these tools. And of course, a lot of people are thinking about that. There's a massive conversation going on at every university, like how should we be thinking about these tools? I don't know. But I have to say, when I'm working with a bunch of undergrad researchers who've never written code before, and the tools have been actually very bad for them because it has been too much of a crutch and they're not understanding how their code works. On the other hand, the expert coders I know, they've benefited enormously. Like, it speeds up. You just write your code faster with these tools. So I don't know. That's a great question.
I think we have time for one more question if someone wants to ask something. Okay. Oh, sorry.
May I take you back to the gibbon there for a second?
Yeah.
So you didn't qualify noise there. Was that artificially manufactured noise, or was that
Yes.
white noise, or
Oh, it's so beautiful.
is there a gibbon in that noise?
No, there's no gibbon in the noise. So this really is, this is an RGB bit pattern. So it's just like bits. And they just added it with a very small, it really is just affecting the low significant bits of this image. So they just modified the low significance bits of this image with that pattern, no gibbon there. The way they found this actually is kind of interesting. There's many ways to find these attacks, but they found this attack in a way that was not intuitive to me. What they did is this noise pattern moves the image maximally away from its neighbors. So they take the neighbors to this image in some neighbor space, and they move this away from its neighbors. And that switched the classification. They didn't try to move it towards gibbon. That was not what they did. So they didn't try to move this in the gibbon direction. They tried to move it in the abnormal direction. So it turns out this image is substantially less normal than that image, but not in a way that you can see. But it happens. So this image, even though it's very confident that it's a gibbon, if you could have asked it, it would say, but it's weird. But there's many different versions of these adversarial attacks. This attack, by the way, was very expensive to find in 2015. Now these are easy to find, but this is called a white box attack in the sense that they had access to the full internals of the model. So they could take derivatives of the model with respect to everything. And so they were searching in directions for like, they could take a derivative of the model and say, this is the direction of worse whatever typicality or whatever that they were looking at. The most exciting area in adversarial attack these days is black box attacks. And that's how people are attacking the self-driving cars, because the self-driving car companies are not going to show you the internals of their code. I think they should have to, actually, for the same reason that RSA is open. I think self-driving cars should be open, but they're not. And so when people are looking at self-driving car attacks, they're actually trying to figure out the attacks without seeing the internals, which is very expensive. But this you can do at home. You can try this at home.
Any other question? Okay. Then thank you, David. It was great.